This, I think, is the last video in this section that maps to chapter 2 of the Nature of Code book. So we're looking at forces in this chapter. We started by just understanding that force is a vector that causes an object with mass to accelerate. We looked at Newton's law. We wrote an apply force function. We figured out we could just make up some forces. This force is this and this force is that. We could calculate some forces. You could make forces that are random, Perlin noise. You could make forces that are based on formulas. And in this last video, what I think is useful to look at here is another case study of a force that has a formula that you find in a physics textbook, gravitational attraction. That's what we're going to look at. And also, I think what's useful to look at with this force is that we have objects that I'm never going to use these again. This is the last video that I'm using these. But this object attracts this object, and this object also attracts this object. How do we have this kind of dance of the particles, so to speak, dance of the gray circles that are moving around our screen? So that's kind of what I want us to look at in the context of this video. Okay, so first, what is the formula for gravitational attraction? Okay. And I should say that what we're doing now is, even though it's all the same, we're taking Earth out of the picture here, right? Every time in all of our previous examples that we were kind of simulating gravity, there was this invisible Earth maybe below the window that was pulling everything down. Now we're actually moving into outer space. This makes no sense whatsoever, but it makes sense in my head. We're moving to outer space, and we're looking at gravitational attraction between bodies. So if you wanted to kind of create the beginnings of a solar system style simulation, you could use some of the stuff we're doing here. Although I should say we're not going to be really rigorous about our scientific accuracy. We just want to look at the formula for gravitational attraction and try to build it into our code loosely. So let's look at that again. The force of gravity equals G times m1, the mass of one object, times the mass of another object, m2, divided by distance squared, and then I'm going to say times r, the unit vector r. So remember, a force has a magnitude and direction. And in this case, this whole section right over here is the magnitude, and r, I'm just sticking r unit vector, that's going to be our direction. So I think I did this backwards. What probably would have made more sense was to start with a diagram. But let's do it backwards. And now let's look at the diagram that maps to this formula. So we have an object, 1, with a mass. So this is object 1, and it has a mass. And this is object 2. It has a mass. And what is r? R is a vector that points all the way from one object to another. Right? So the gravitational force on object 1 is a vector that points from 1 to 2. The gravitational force on object 2 is a vector that points from 2 to 1. But let's just actually make things simple to start with. In our example, we're going to have something called an attractor that doesn't move, and we're going to have, this is our mover. Okay? So the attractor is this fixed thing, and the force is going to map from mover to the attractor. Okay, so we kind of did this now. This is it. This is r. What's the direction of the force? It's r. It's r normalized. Okay. We have to. I got it. I got it. This is what we're doing, right? Hopefully we understand this diagram. It's pretty simple. This thing is being pulled to that thing. This is the magnitude. That's the direction. We need to write this in code. So how do we get a vector that points from one location to another location? I wish you were here because you would totally answer this question now, and I also wouldn't be so lonely. But anyway, so what we can get, the answer is subtraction. We can subtract location 2 minus location 1 gives us r. So what I'm going to do is right up here, I'm going to make a vector called direction, and it is going to equal, I'm not going to have enough room on this board, but I'm going to write down here, p vector dot subtract, and I'm going to just say location 2 minus location 1. So I'm kind of making up that variables exist. We'll go look at a practical example in a second. But assume that we had 2 location vectors. The direction is the difference. A vector that points from 1 to 2 is location 2 minus location 1. But we need to normalize it. So now we can say dir dot normalize. and dir is the direction. That's the unit vector r. We're done. So we have the force's direction. Once we have the force's direction, we just need to scale it according to its magnitude. What is its magnitude? G times n1 times n2 divided by distance squared. So a couple things here. What is G? G is the universal gravitational constant. It's some number that I absolutely do not have memorized because I like program things in processing. I don't actually like look at stuff in the real world and how it interacts. So, we don't need the real world number in our processing code. That is a constant. What we can use that constant for is the force strong? Is the force strong or is it weak? How is that force? So for right now, we could say G is 1 or whatever. It's some but constant, but we could, and I'm going to, I don't like to use, it's going to be, it's fine. It gives me a little anxiety to make a variable that's a capital letter because, that could be breaking some conventions, but let's just do it for effect right here. So I'm going to say G is 1. Now, mass of 1 and mass of 2, those are going to be constants, variables, scalar quantities, floats. So we could assume that we have mass 1 and mass 2. And distance. What is the distance between location 1 and location 2? Well, processing has a distance function that we could use. Processing also has a distance function to give us the distance between vectors. But if you remember, what did we do right here? We said, give me a vector that points all the way from object 1 to object 2. Then we normalized it. What we could do is say, hey, right before we normalize that vector, what is its magnitude, right? The magnitude of a vector that points all the way from 1 to 2, the magnitude of that vector, that's the distance between those two objects. So right up here, now this is where we really need to insert a line of code. We could say float d equals dir dot magnitude. And if I wanted to, this is what I kind of fumbled in the last video, but there is a method in processing called mag squared, which will actually give you the magnitude squared. But maybe for right now, for simplicity, I won't use that. But that'll optimize the code a little bit if we use that. Okay, so now that we have that, dir multiplied times g times the mass of object 1 times the mass of object 2 divided by d times d. So this is the magnitude as it maps to this formula. And again, we have something very special here. It's very special and nice about this. What we're doing, remember, I'm not suggesting that gravitational attraction is like this force that's going to make all these magical, beautiful, wonderful projects. What I am suggesting is that you, coming up with a creative way of calculating a force, might be able to create a behavior, an emotional quality, some form of interaction that's going to be successful in a project that you're making. What's interesting about this force is divided by distance squared. The further the objects are away, the weaker the force. The closer they are, the stronger the force. Maybe you want to do something different. Maybe you want a force that's weak when they're close, but strong when they're far. Maybe you're creating some type of these circles on the screen that are in love, and the further apart they way, the more they must come back together. But once they're together, they can just kind of be, I don't know what I'm talking about here. But we should all aspire to create love in our processing sketches. So, okay, but the point of what I'm saying here is this divided by distance squared, again, we're seeing the properties of the system itself are informing the magnitude of that force. And how you build that into things you make is very important, I think. So, okay, so now that we have this, we can look at how do we apply this in code. Now, here's the thing. I feel a little anxious about this because I don't really know where this is going, but I'm going to tiptoe slowly over here. And we do have a processing sketch that we can look at. Now, it's actually not going to run because I deleted some code out of it. And I'm going to just save, I should have done this before, but I'm just going to save it as, I'm working with, in the Nature of Code book, this is example 2.6, simple attraction. So that's the example I'm working with here. And if we run it, we're going to see it can't find this method attract. This is the method that I want us to add to this program together. I guess it's really just me, but let's feel like we're doing it together in this video. So one thing I should point out about this is that we have both an attractor and a mover. So we have two separate objects. And in fact, if I just briefly for a second comment out this part that we're eventually going to use, and I run this, we can see this is our sketch. We have this attractor in the center, and we have this mover up top. And we want the mover to experience a force that where it's attracted to the object. And I shouldn't have commented, I just noticed I shouldn't have commented m.update. What's really happening here is that mover is moving to the right. So instead of just moving at a constant velocity to the right, we want it to be attracted, pulled into that object. Okay, so how do we do that? So this is what I'm talking about in terms of nice object-oriented programming syntax. This is only one way of doing it. There are countless ways you could organize your code, but what we're doing here is we're saying, hey, the attractor has a method that can receive a mover, calculate a force, and then we can store that force in a variable and apply it to the mover. So we're having objects communicate by saying the attractor attracts the mover. Okay? So what this tells us, let's actually, I don't know where we are in time. This is 9 minutes so far, so I'm going to belabor this point for a second. So if I come back over here, if you're really familiar with object-oriented programming, you might want to just kind of skip ahead a couple minutes, but I'm gonna just cover this, I think, because it's kind of important. We wrote code that says a.attract m, and the result of that gets stored in a vector. So this is, I think, a nice strategy. A is an attractor object, m is a mover object, and this kind of reads nicely. It says, attractor attract the mover, return that force, and then we can say mover.apply force F. That force can then get sent back into the mover. Now, okay, so what's going on here? We wrote this code, but we haven't written the attract function. It doesn't just magically exist, right? There's no attract function just magically in an attractor class. But we wrote it this way as kind of an indicator to us that what is the function we need to define? The function we need to define is called attract. It receives a mover object, which I'm going to call other, and it returns a p-vector. So this here is that method signature. It's a function called attract that's going to go in the attractor class. It's going to receive a mover object, and it's going to return a p-vector. So I just wanted to go over this kind of, this is important. This is kind of how we have a nice way we can have objects communicate with each other by having one object receive the other one as an argument to the function, and then they can, do stuff in that function together. Okay, let's go back and let's put this into our code now. Okay, so if we go into the attractor class, we now need to write a function called attract, which receives a mover as its argument. These things are going to fall off this little podium. Okay, so we're going to write a function called attract. The mover is its argument. It's going to return a p-vector. So what's the first thing we need to do? We need to know the direction of that force. So I'm actually going to just make a variable called force, which equals, we're going to subtract the mover's the location of the attractor minus the mover's location. Now notice here we're in the attractor object. So since we're in the attractor object, its location is just location. The mover's location is the argument. The mover is the argument, so we need to refer to that mover m's location. So the attractor's location minus the mover's location. Then we're going to normalize that, and then this is so we have the direction. This is us, direction of the force. That's the direction. Now, once we have the direction, we need the magnitude. Magnitude of the force. So what is the magnitude? It is, I'll call it strength, equals g times the attractor's mass, which is just mass, times the mover's mass, which is m dot at mass, divided by, and to be safe here, let's put some parentheses around here, divided by distance squared. Now, notice if we run this, it's going to say it can't find anything named d. So d is the thing that we haven't actually calculated yet. But remember, distance, we have a vector pointing from the one location's object to the other one object's location to the other object's location. We've got a vector pointing between those two. The length of that vector is the distance between the two. So right before we normalized force, we could say, hey, what is your magnitude? So this is us saying, hey, we're getting that vector. We want to normalize it, but before we normalize it, just wait a second. Can we please have your length? Because that's the distance. Once we have that, this will work. All we need to do is then put magnitude and direction together by multiplying by that strength, and I think I spelled it wrong. So this is putting magnitude magnitude and direction together. And now we have force multiplied by strength. So this is the direction, this is the magnitude, this is them together. Let's say return force, and do we have everything on? We have all that commented back in. We're getting the force, we're applying it, we're updating it. Let's run this. It's going to be very dramatic and exciting, and goodbye. Okay, so what happened here? It didn't seem to work. So let's go back and look at this code again. Why might this not have worked? It's really tragic because we really were very careful to put everything in here. Here's the thing. I have something to mention. This is not the real world, right? That's a little gray pixel circle on the screen. This is some made-up code. We're kind of crazy. This is where we have to say, you know what? The real world has this formula, but we want to make the appearance of something. We've got to kind of adjust and tweak here. And what's the problem? The problem is that distance times distance in pixels can be really large. And as soon as these objects get like 150, 200, 250 pixels away, that force is so weak that it's just floating off into the distance. At the same time, when the object gets so close, that force could suddenly become so large that some really strange behavior could happen. So this is a nice moment where we could use the constrain function. We can kind of constrain our world in an unrealistic way, but in a way that's going to just make us feel happier in our lives. So let's do that. We're going to say, I know this is the actual distance, but what I want to do is constrain that, I'm going to say between 5 and 25. So even if you're more than 25 pixels away, just consider yourself as 25 pixels away. Note, I'm not actually constraining its location. It can be anywhere it wants to be. I'm constraining the result of that distance calculation. So now if we run this, again, you can see, we get this kind of attraction behavior. So you can see it's like this almost orbiting around of the attractor in the center. So this is really it in terms of getting that gravitational force to work. But I want to just, we can see here we have the attractor, which is fixed. And actually, if you go and look at this example, one thing you'll see is this attractor can actually be moved, which I think is kind of a useful thing to look at. But you can look at the code for how that's done. But what I want to look at, though, however, is one thing that this example isn't doing. So this example is saying, hey, have an attractor attract a mover. And if we wanted to, we could expand that very quickly by, I must change the size of the sketch. We could expand that very quickly by having a lot of objects be attracted to that singular attractor. So here we can see like, we could do that in a loop. We could say, hey, all of the movers, every mover I be attracted to the attractor. So that's a sort of instant change. We have a single attractor, we have an array of attractors. But what's a little bit more difficult is, and you can kind of consider this as an exercise for yourself, I guess, is how do you have mutual attraction? Every object is attracted to every other object. A hint of that is you need a nested loop. For every mover, be attracted to every other mover. So for every mover again. And then, of course, you want to make sure that one mover is not any mover is not attracted to itself. So you need to build in something for that. And if you're looking for the answer to that, it is example in the 2.8. So if you're following along the book, example 2.8 will show you that mutual attraction. And one thing you might think about to go beyond that is, A, how could you do that in 3D? And B, I'm looking at these, how could you change that force from an attraction force to a repulsion force? And could you have objects attracted to something in the center but repelled from each other? How could you mix this up to create a dynamic system with multiple different behaviors happening at the same time? Just while we're here, I also thought that I would just kind of quickly bring up this kind of a classic project of use of attractors. This is called Metropop Denim. I actually forgot the year, but this is Clayton Cubitt and Tom Carden. This is from many, many years ago. I think this was done with like the alpha version of processing. So that's before, before this 2.0 beta, before 1.0, et cetera, before 1.0 beta. So, but you can see that there is, if you were to trace the pathways of particles being attracted to maybe invisible attractors, you can create these kind of patterns, and these patterns were combined with fashion photography to create these spreads for a magazine. And really, I don't know if they did this with the project, but you could imagine positioning the attractors according to some properties of the photographic imagery in such a way. So there's lots of possibilities that you can use this for, and so, I don't know, have a good time trying this stuff out and leave some comments or ask some questions or I don't know, something. This is the end of chapter 2. In the next set of videos, which will all be numbered 3 point something, we'll be looking at oscillating motion and reviewing trigonometry. Seacrest out. Is that something I can say? I'm not Brian Seacrest, so that doesn't make any sense. Okay, goodbye.